As I was saying, before I forgot the memory card today and started late, I was going to give you a sports story from my childhood. I'll give you one on Wednesday. Probably one on Friday too. Lots of fun little stories from my past. But we better get going with the content here today. Lecture 33. I will review vector spaces, focusing on things I didn't really focus on as much as I wanted to when I made the lecture last Thursday. So we can emphasize some things more. And hopefully if we have time, we'll have time to start field extensions during 33A. But definitely in 33B, field extensions, that's the big thing. And then something called splitting fields and some examples and theorems. It's pretty hard abstract stuff there, but if you think about the examples, it definitely makes it more down to earth and understandable. Okay? So again, let's review vector spaces. I'm going to go quickly, very quickly through this first slide, but this is content you should know. I'm describing vector spaces more verbally, whereas in the book they're described more with symbols. V is said to be a vector space over a field F. Okay, first thing to realize here is you've got two sets, V and F. V is going to be the vector space. F is going to be a field. That's, of course, then going to have two binary operations, addition and multiplication in the field. V itself, though, has a binary operation, addition. It's an abelian group under addition. Vector spaces could be rings or fields, but when we think of them as vector spaces, we ignore any multiplication of vectors we might do. We only think about adding them. But we do think about a scalar multiplication, or as I sometimes say, a scalar slash vector multiplication, where you write the scalar next to the vector. I write AV, where V is understood to be a vector and A is understood to be a scalar. This is an element of capital V, and this is an element of the field, capital F. And that's supposed to denote scalar multiplication. In analogy with what you learned in linear algebra, if the field happens to be the field of real numbers, A does scale the vector, right, up or down. You're multiplying it by 2, for example. If you imagine the vector as being an arrow, you get a vector that's twice as long. If A is 1/3, you get a vector that's 1/3 as long as the original. If A is -5, then it's 5 times longer than the original and pointing in the opposite direction. But here we're thinking of vectors as purely algebraic objects. We don't have to think about the geometry, though that can be helpful. The scalar multiplication satisfies closure, as you would hope. Distributive property of scalar slash vector multiplication over vector addition. I mentioned this last video that when you say over vector addition, that means you are adding the vectors. And the distributive property in that case looks like this. But then there's also a distributive property of scalar slash vector multiplication over scalar addition. You've got two scalars, A and B, that are being added before you multiply by the vector V. You could multiply the vector by the scalars first and then add the results. These are two distinct properties. They are both a kind of distributive property, though they're not exactly the same. Reserving letters near the beginning of the alphabet for scalars from the field F, and letters closer to the end of the alphabet, V, U, W, maybe X, Y, Z for vectors. Associativity means this. Again, realize what's going on here. This is a product in the field F. A and B are field elements. This is A times B in F. Times the vector, this is the scalar slash vector multiplication, giving you, in the end, a vector. That scalar slash vector multiplication here, same with this, but you get the same thing. That's what that property says, associativity. And the scalar one from F does act like a multiplicative identity. You multiply it times any vector V, you will get that vector back. But in general, here we are talking about F being an arbitrary field, not the real numbers necessarily. Could be a finite field. And you can still talk about vector spaces over that field. And you can still prove things based on certain definitions, like linear dependence and independence. So here, compared to the lecture from last week that I made, I'm going a lot faster now. I did some other things in between the first slide I just showed you and this slide, the slide I'm about to show you. I want to emphasize some different things, give you more time to sink in about linear dependence and independence, for example, and the idea of a basis. Okay, you ready? Here goes. A set of vectors S is said to be linearly dependent. Technically, you should also emphasize what the field is, over the field F. V could be a vector space over two different fields. That's possible. Which really means it's two different vector spaces. It would be the same set V, but possibly two different fields. This set could be linearly dependent over one field, but not the other. That's a possibility. So you always, in this theory here, want to emphasize it's over the given field that you're talking about. If there are vectors v1 through vn from S and elements a1 through an from F, not all zero, super duper extra emphasis there, such that linear combination, these things are called linear combination, gives you the zero vector. A set that is not linearly dependent is called linearly independent. As you remember from linear algebra, these are very important terms. Okay? Fundamental to understanding vector spaces, you have to understand the idea of linear dependence and independence, in this case, over the given field. In linear algebra, we don't bother typically saying over the field because it's always assumed to be the real numbers, at least the way we teach it here at Bethel. Sometimes you can take linear algebra classes where they take the field to be the complex numbers, but we almost always take the field to be the real numbers in that class. For extra emphasis, you can think of this another way. This finite set, for example, is going to form a linearly dependent set if this equation, where you think of the a's as being unknowns, like x's perhaps instead, has a non-trivial solution. Whereas with a linearly independent set, that equation, that homogeneous equation where the right-hand side is 0, is only going to have the trivial solution. All the a's would have to be 0. Let's do an example. And here we'll come back to a familiar vector space from linear algebra. Come back to a vector space, the vector space V equals R3, three-dimensional space, over F equals R. You write down 3 vectors in R3 at random, so to speak. In all likelihood, do you remember from linear algebra, do you think they're likely to be linearly independent or linearly dependent? If I write down 3 pseudo-random vectors from R3, what do you think? Do you think they'd be linearly independent or dependent? I'll write them as column vectors. Just making these up on the spur of the moment here. What do you think? Do you think, probability-wise, do you think those are likely to be linearly independent or linearly dependent? Do you remember? You have the intuition there? Nobody want to take a stab at it? And how would you tell? Nobody? In all likelihood, since I wrote those numbers down somewhat randomly, they're most likely to be linearly independent. How would you tell? There's a number of ways. You could make them to be column vectors of a 3x3 matrix. Which I'm about to do here in Mathematica. Or row vectors for that matter, it doesn't matter. But I'll make them column vectors. So I'm looking at the first components across the top row here, and then the second components across the second row, and then the third components across the third row. What kinds of things can I do to this matrix to confirm that these are probably linearly independent? Remember the linear algebra, the really long theorem with all those parts? Inverse matrix theorem. Has like 20 parts to it by the end of the book. What's something I can check with a determinant, for example? If these are going to be linearly independent, what should the determinant be? If it's likely to be linearly independent, you would think it would not be equal to 0, and that would be the case. Not equal to 0, 41 in this case. That would be one way to confirm these three vectors are linearly independent. The determinant being non-zero means the matrix equation AX equals 0 can be solved by using the inverse of A. The determinant being non-zero means A inverse is going to exist. And I can write this, and A inverse of 0 is 0, and this simplifies to X, meaning this equation being true when A inverse exists means you only have a trivial solution. Therefore, the columns of the matrix must be linearly independent. You could also row reduce the matrix. Row reduce. And sometimes you'd row reduce it with an extra column where you'd have zeros on the right to emphasize that you're solving a homogeneous system. But we can just imagine that we've put zeros there. We don't actually have to look from there. You get a pivot in every column, right? Pivot position. If you had a bunch of zeros there, you'd add another column of zeros. There would not be a pivot in every column in that case, but that's okay. That's an augmented matrix. The zeros on the right are just the right-hand side of the system of equations you're solving. It would imply a unique solution, x equals 0, y equals 0, z equals 0. Funny thing about this arbitrariness is that one matrix that you would think is kind of arbitrary in a sense is definitely not. I found this out one day when I was teaching linear algebra, and I was sort of talking about this kind of stuff. And I'm like, oh yeah, you wrote down an arbitrary matrix, it's likely to be invertible, a square matrix like this. And so I typed in 1, 2, 3, 4, 5, 6, 7, 8, 9. And lo and behold, that matrix is not invertible. When you row reduce it, you get a row of zeros. Its determinant is 0. So if you ever teach linear algebra, don't use that as an example. This would be an example, even though it doesn't look like it necessarily, of three vectors that are linearly dependent in R3. I made them go across the rows. I could have made it go with the columns. I could have gone 1, 2, 3, 4, 5, 6, 7, 8, 9. I'd still get a matrix with a determinant of 0, a matrix and its transpose. Or if one's not invertible, the other one won't be either. If you're talking about square matrices. Okay? So bringing back some memories of linear algebra. Maybe those are good memories compared to other things in linear algebra, right? Maybe. Next slide, basis and dimension. Let V be a vector space over a field. Always mention the field in this class. It's going to be important. We will see how it's important as we go through today and the rest of this week. A subset B of V is called a basis for V. If B satisfies two conditions, it's a linearly independent set over F. And furthermore, every element of V is a linear combination of elements in V. It spans the vector space. These conditions actually are enough to imply that every element of V is a unique linear combination of the elements of the basis. And this is part of what can justify the use of what are called coordinate vectors, which I will talk about in more depth here today than I did in lecture 32. I'll come back to that. You can basically use the idea of coordinate vectors in an abstract setting to help you relate abstract vector spaces to something you can work with, matrices and column vectors, for example, or row vectors. Here's the big theorem, the main theorem of this section. If you've got two different bases of the same vector space over the same field, then they have to have the same number of elements, and we are talking a finite number of elements is the assumed thing here. This vector, we haven't specified that there's a V, but there is one in the background. There's a capital V here. And you're assuming these two finite sets are both bases of that vector space V over the same field F. Then M has to equal M. These have to have the same number of elements. And then this theorem justifies the idea of dimension. This definition doesn't make sense without this theorem. A vector space that has a basis consisting of n elements is said to have dimension n, and is said to be finite dimensional. So the definition of dimension in the finite dimensional case is it's the number of elements in any basis. And there's always more than one basis, okay? And it's partially in the applications of linear algebra. It's partially the choice of basis that helps you solve a problem, in part. You remember change of basis and diagonalization? Using eigenvalues and eigenvectors. And if you took diffeq from me, which many of you did, we used eigenvalues and eigenvectors. That was really a change of basis that allows you to, for example, solve a system of differential equations more easily using the eigenvalues and eigenvectors. So changing a basis is part of the point of applications of linear algebra. So you have many bases for a given vector space. Vector spaces which, as sets are infinite, you're going to have infinitely many bases. Unless F is the trivial vector field, but we don't want that to be the case. By definition, the trivial vector space 0 doesn't have a basis, or you could say the basis is the empty set. The book mentions that. But by definition, we say that's zero-dimensional. And if there's no finite basis, and there are plenty of examples where there is no finite basis, then the vector space is said to be infinite dimensional. Here's another application to differential equations, actually. Consider the differential equation diffeq. Let's make it a second order differential equation. The second derivative of y with respect to t twice plus 5 times the derivative of y with respect to t plus 6 times y equals 0. I could say let V equal the solution space. What do I mean by that? I mean the set of all functions, solutions of differential equations are functions, that satisfy the differential equation. The set of all functions, I'll go ahead and write f of t here, even though that's really the output of the function. These are sufficiently nice real valued functions of a real variable by sufficiently nice, in this case, it means the second derivative exists and ideally is taken to be continuous. Set of all such functions satisfying the property that their second derivative plus 5 times their first derivative plus 6 times the original function always equals 0 for all t. For all real t, say. That can be called the solution space. In this case, the elements are functions. This is a vector space. This is a vector space over the field of real numbers. Is it infinite dimensional or finite dimensional? And if it's finite dimensional, what's the dimension? What's the basis? Well, sets of functions in general, if I didn't put any conditions like this on them, are infinite dimensional. If I consider the set of all continuous functions on the real line, for example. That's an infinite dimensional vector space. And by the way, it is a vector space because I can add functions and I can multiply them by scalars and it would satisfy all the properties of a vector space. But I've got extra conditions on these functions. They have to satisfy this differential equation. So is that enough to make it finite dimensional? Actually it is. And the dimension turns out to be 2. This is a 2-dimensional vector space. V is a 2-dimensional vector space over R. What would be a base? What would be a basis? People who took DiffEq should be able to look at this and give me a basis. You say, huh? I don't remember doing that in DiffEq. Yes, you did. You just didn't think of it in terms of linear algebra. What do you think I have to do to help me find a basis for this? The solution space, the set of all functions that solve the differential equation. You're off the hook because you didn't take DiffEq. Remember solving equations like this? Hooke's law, mass in a spring with damping. You get some oscillations perhaps if the damping is small. You get no oscillation, you get exponential decay if the damping is large enough. What if I said find the general solution? Could you do that? What do we always guess with those kinds of equations for the solution? I said the word exponential. Maybe e to the x. Yeah, well, actually it's good enough initially just to guess something like that, e to the st. You could put an a in front of it, that's right as well. But actually the a wouldn't matter. It's the arbitrary s that matters. S actually can't be arbitrary, we have to solve for it. You got to find the derivative of this. And the second derivative, plug it into the differential equation, solve for s. And it's not guaranteed to work a priori here, but it does work. There are 2 values of s that make this work. I want this to equal 0 for all s. I can factor out an e to the 5t from everything. The only way this is going to be 0 for all t is if this thing right there is 0, because e to that power is never 0. This means s squared plus 5s plus 6 must be 0. That's an algebra equation that can be factored. S could be -2 or -3. And that does mean that e to the -2t and e to the -3t are solutions. And in fact, the set consisting of those two functions is a basis for this vector space. This is a basis for V because everything in V, every solution, can be written as a linear combination of those two things. That should ring a bell from Q. The general solution is an arbitrary linear combination of those things. Okay, that takes proof, but I'm just saying this is true. The solution space is two-dimensional. Two-dimensional vector space. If I made it a third-order equation, it would be a three-dimensional vector space. If I made it a fourth-order equation with fourth derivatives, it would be a four-dimensional vector space. It is important that the equation is special in that it's linear. I'm not going to say what that means, but it's a relatively simple kind of equation that's going to make this work. But that is the gist of it. You can relate it to stuff about vector spaces and dimension. Other worthwhile facts to know. If you've got a linearly dependent set of vectors, and then you can say one of these vectors is a linear combination of the others. I guess I'm going faster now again because we have the quiz. So, if you've got a collection of vectors that's linearly dependent, and you'd like to get a basis out of it, just start throwing some vectors away until you get a linearly independent set. It would then be a basis for some subspace of the vector space. And that's essentially what this theorem says. If you've got a collection of vectors that spans a vector space, meaning every vector in the vector space is a linear combination of these, then some subset is a basis. There's going to be some subset that's linearly independent still, well, that is linearly independent and still spans the vector space. These are all definitely useful facts to know as you start embarking on chapters 20, 21, and 22. Every independent set is contained in a basis. If you've got a finite dimensional vector space and you've got a collection of n vectors that are linearly independent, maybe they don't span the space yet. If they don't, you can add vectors to the collection to have a basis. It's still going to be a linearly independent set. You got to be careful how you add the vectors. You can't just add arbitrary w's here. But you, in theory, you can add vectors to the given set to make a basis. And then finally, exercise 31 is the idea of coordinate vectors. I would like to spend time with this, and here about that it wasn't quite complete. I would like to spend time with this, but I think not today. So we're going to take the quiz here in a minute. I think we'll come back to this on Wednesday, because it is something I think is worthwhile emphasizing. Okay? But we'll take the quiz right now.